we dive in, let's chart our course. These slides give you a roadmap of what you will walk away with. Core concepts, actually the core concepts of the HQ curves. HQ, H stands for head, Q stands for the flow rate. We will go through cavitation and the related net positive suction head that will prevent cavitation. Cavitation is a damage and we will describe it later on. So there is a net positive suction head that should be there to ensure that our pump will not be in a risk situation and cavitation will not happen. So these objectives are where theory meets the field and where your understanding becomes practical. Pump performance curve. Let's start with the heartbeat of a centrifugal pump, which is the HQ curve. The relationship between the head and the Q, it is an inverse relationship which is illustrated with a curve. When we say inverse relationship, we mean that as the flow increases, the head decreases and vice versa. The curve that we will see shows the relationship between the pressure the pump can build, which is the head, and how much flow it is producing. So it's like a seesaw, as I just told you. More flow, less head. Understand this and you are halfway to selecting the right pump. Head is an energy the pump can add to the fluid. Of course, it is in meters. How can energy be in meters? We have to stand on this point for a second. Meters of head is a way to express how much specific energy the pump gives to the fluid. So it is a specific energy, that is energy per weight. And Q is the flow rate, which is the volume moved by the pump per unit time. Can be liter per second units, or can be meter cube per hour, or GPM, which is gallons per minute. Let's go to the curve and try to understand it. This red curve shows the relationship between head and Q. Curve starts high on the left and then drops gradually to the right. It drops gradually to the right, and this shows that as flows increase, head decreases. For example, Q1, the head is H1. If you increase to Q2, the head will be H2, which is less than H1. So it shows the inverse relation between the head and the flow rate. So why it is inverse relationship? Why the curve is like this? Why? This is because friction and losses in the impeller, volute, and the pipe network, all these frictions will lead to losing the head the pump can produce. The pump loses its ability to push the fluid to high elevation because of these frictions. Some important point we need to clarify on this diagram is the shut-off head. This is the shut-off head. It is the maximum head at zero flow. As you can see, it is the maximum head at zero flow. And we get this head by closing a valve. If you imagine the pump is running, delivering flow, and if you close the valve at the discharge line, you can read the pressure or the head through a gauge meter. So this will always be the maximum head your pump can produce. Okay, don't afraid, it's not dangerous if you are applying a centrifugal pump and you shut off the valve. But if you are using a reciprocating pump, we will discuss this later on, you have to be very careful, and there should be some relief valve to prevent excessive pressure buildup. Static versus dynamic head. In pumping systems, understanding the static head and dynamic head is essential for selecting and sizing pumps properly. You have to understand very well the static head and the dynamic head. So let's start with the static head. Head is more than just height. Static head is the elevation difference, like lifting water from a basement. So it is an elevation difference. It is like the distance between the height and the delivery. And the static head is divided into suction head and discharge head. Static suction head or lift is a vertical height from the pump center line to the liquid surface on the suction line. Okay, here it is. The static suction head, it is here, from the liquid surface to the center line of the pump. Okay. Static discharge head. Static discharge head is from the center line of the pump all the way to the discharge point, which is here. So this is the static discharge head, and this is the static suction head. Okay. So the total static head is the summation of the static suction head and the static discharge head. Very important to know that the static head is independent of the flow rate. It exists even if the pump is off, and can be positive if it is a head, and can be negative if it is a lift. For example, here this is a lift, okay, because we are taking water from a level below the pump, so we consider it a lift. That is why it should be a negative sign. And the static discharge head, it is above the pump level, so it is a positive. So to get the total static head, we add the static and the suction, but with the sign. And if you want to talk about the dynamic head adds the fight against friction. So all frictions will be counted for by the dynamic head. Frictions from the pipe roughness, from elbows, from fittings. So mastering this helps you size pump and save energy. Dynamic head is a head due to friction losses, and it is equal to the friction losses in the suction and the discharge pipes. This is suction pipe. You add the friction losses here plus those friction losses in the discharge. Okay, that will give you the dynamic head. Okay, I'm talking about the total dynamic head is the total head the pump is developing while running, while delivering flow. It's called the total dynamic head, and basically it is the total static head. It is the total static head plus the dynamic head, which is due to friction. So you add the friction plus the total dynamic head, you get the total static head plus the friction head will give you the total dynamic head. Positive displacement pump curve. Positive displacement pumps are like bulldozers, you know. They push a fixed volume no matter what. Whatever amount of fluid, they will push it, no matter what is its density, what its volume, what is. But in real life, a bit of slip happens, especially with compressible fluids or high pressures. Like, in the positive displacement pump, one of the example of positive displacement pump is a piston and cylinder. So you push your fluid by the piston. So it will create high pressure. And because of this high pressure, slips happens. Okay, so always we say that slip is due to leakage or if your fluid is compressible. So ideally the head Q or the head and flow relationship for a positive displacement pump is that always the flow is constant regardless of the head. Okay, and if we make a quick comparison between positive displacement pump and centrifugal pump, we can understand this more. Flow versus pressure, we say that in centrifugal pump, we just discussed that is a curved line. It is inverse relationship, downward slope. For the positive displacement pump, as we will see in next slide, the curve is nearly vertical, which means that you make a vertical line from the Q axis. So you will fix it on one value of Q, that is constant flow, regardless of the head. The flow do not change with pressure in positive displacement pump. Okay, the flow is always constant while the pressure will increase or decrease, but the flow is constant. In pumps, in centrifugal pumps, of course, yes, the pressure drops or the flow drops with higher head. We can always say that positive displacement pumps are suitable for high pressure, low flow. It withstand high pressure. But in centrifugal pump, this is suitable for high flow, low to moderate pressure. The shut-off condition that we discussed on the last slide, and we said that it is dangerous in positive displacement pump because the pressure keeps rising, while it is safe in centrifugal pump as the flow stops at shut-off. Here is the positive displacement pump curve. the flow is almost independent of the system pressure. It shows a vertical or nearly vertical line on the head versus Q graph. Head pressure varies with system's resistance. So, friction, back pressure, fittings, and so on. So, if the system pressure increases, for example, closing a valve, the pressure output rises sharply, but flow stays almost the same unless relief valve opens. So here again, the vertical line shows constant flow. If the line slopes slightly, like this, if the line comes and slopes slightly, it is because of a slip, which is due to some internal leakage, especially at high pressure. Leakage that happens through the gasket of the piston, or through any clearance between the piston and the cylinder. So this leakage happens especially in very high pressure. And in these systems, you have always to use a relief valve to protect the system from rising to extremely high pressure that may result in damaging your pump. Centrifugal pump head losses. No pump is perfect. Internal turbulences, leakage passes, and impeller inefficiencies all eat away at your ideal head. This slide is about recognizing where those losses occur and why the actual performance is less than perfect and what you can do about it. In any system using a centrifugal pump, the total energy, which is the head, the pump must overcome is more than just lifting water vertically. It also includes losses due to frictions and fittings in the piping network. And as you can see here, types of head losses in centrifugal pumps. We divide them into almost 4 types: major losses, minor losses, losses due to velocity head, static head. Static head itself is not a loss, but it is still part that the pump must overcome. Now, the major losses is mainly friction losses caused by the fluid friction along the length of the pipe. So, friction depends on the pipe length and diameter. If you are using long pipe lengths, you will get much friction losses. And the same, if you are using smaller pipes compared to larger pipe diameters, you will get also more friction losses. Also velocity. Frictions depends on the velocity. The more the fluid velocity, the more the friction losses. And of course, the roughness. Like if you are using a PVC, which is a smooth surface, you will reduce the losses compared to using black steel pipes. That's why whenever we can use plastic pipes or PVC pipes, it is better than using rough surface pipes. And the friction losses is calculated by the Darcy web batch equation. So HF stands for the friction loss head. It is equal to the friction value, friction factor, multiplied by the length of the pipe divided by the diameter, multiplied by the velocity square divided by 2 times acceleration due to gravity. And from here it is very clear that the friction losses directly depend on the friction, and the length of the pipes increases directly with these two factors, and indirectly to the diameter because it is on the fraction. Minor losses is caused by the fittings like elbows, bends, valves, and other components. And the minor losses head, HM, is calculated by multiplying the loss coefficients of all these fittings times V square over 2G. The third head loss is the velocity head. Velocity is related to motion, which is the kinetic energy. Sometimes we include it in the total dynamic head. And the velocity head is simply V square over 2G. And the static head, as I just said, that it's not a head, but it is part of what the pump must overcome. So the total dynamic head that the pump must develop is equal to the total static head plus friction losses, which is the major losses, plus the minor losses from the fittings, elbows, bends, and so on. Let's see a diagram that explain in a clear way the pump head. You can see this is a total head. This total head is what you use to select the proper centrifugal pump. By the way, if the head is underestimated, the pump may not deliver the required flow, and you will be losing what you are intending to deliver. So generally we need to minimize the losses. So how are you gonna generally, what techniques you use to minimize the losses? You can use, as we just discussed, larger pipes as much as possible to reduce what? The velocity. Because increasing the velocity, increasing the friction losses. Always try to minimize the number of the bends, because many losses happens because of the bends, elbows here, here. So as much as possible, try to use less fittings. And most important, select a smooth pipe. Select a smooth pipe. Can go for PVC, plastic pipes as much as possible. Use efficient piping layout, like shorter runs as much as possible. If you can reduce the pipe lengths, you are reducing the friction losses and the head losses. Pump power equation. Let's translate pump action into mass. This formula, power is equal to rho, density of the fluid, times Q, the flow rate, times G, acceleration due to gravity, times H, which is head. This formula combines flow, head, fluid density, gravity, and efficiency if provided to calculate the required power. It is how you measure your motor is sized right. To make sure that your motor is sized right, you have to do these calculations. And to avoid burning energy for nothing, like getting a bigger motor for nothing, lose of energy. Okay, so this is the power. Actually, we have 3 powers that we need to consider when we are applying pumps. Hydraulic power, which is water horsepower, and this is the ideal power required to lift or move the fluid, ignoring losses. Just the power to move the fluid without losses, as if there is no friction, as if there is smooth surfaces, big pipes, short lengths, no friction losses. In this case, we use the hydraulic power, and it is simply the density, the fluid times G times Q times H will get you the hydraulic power. The shaft power, input power to the pump. This is the power supplied to the pump shaft, and this power will account for the pump efficiency. Like it shows you how much power is delivered to the shaft. Like it shows you the pump efficiency, how much the pump is able to convert the input power, which is the electricity, into a shaft power. So it is simply the hydraulic power, which is the power that should be provided by the pump, but it will not provide this calculated hydraulic power because of some losses, and we divide it by the efficiency because it is not 100% efficiency. If your pump is 100% efficiency, means that all the power in will be converted to the shaft, then this will be 1. But actually, it is less, like 80%, 75%, 60%. So you will add this percentage here. Okay. The motor power, it is input power to the motor. If you are sizing the motor, it accounts for the motor efficiency, like shaft divided by the motor efficiency to give you the final power. Again, efficiency is the useful power divided by the supplied power. So, to get the overall pump efficiency, you have to multiply the hydraulic power output to divide it by the shaft power input to get the overall pump efficiency. This tells you how efficiently a pump converts a mechanical energy into fluid energy. So is this clear? To get the pump efficiency, and we already stated that on the last slide, that the motor power is equal to the shaft power divided by the motor efficiency, and the shaft power is equal to the hydraulic power divided by the pump efficiency. So if you know the hydraulic power, if you know the shaft power, divide the hydraulic by the shaft power to get the pump efficiency. Now let's see the types of losses in hydraulic losses. And the hydraulic losses are caused by friction and turbulence inside the pump. So it's not the losses related to the pipes or fittings or rough surfaces of the pipes. It is inside the pump passages, the impeller, the volute, and so on. So this is what causes the hydraulic losses, which leads to pressure drop and reduce the output. This hydraulic losses increases with poor design of the pump itself, like if they are making inside the pump sharp bends, or the surface of the pump inside is rough and so on. This all leads to increasing the hydraulic losses. The other type of losses is mechanical losses. And mechanical losses are due to friction in bearings, seals, and shaft alignment. So all these are mechanical. Again, losses in the friction in the bearings, okay, and the seals. And if the shaft is not aligned, this all leads to an increase in the mechanical losses. Okay, we have volumetric losses, okay, which is the slip. Fluid leaks back from the discharge to the suction, and this is common in positive displacement pump, and of course it increases with pressure. Disc friction losses. Disc friction losses is specifically happening in centrifugal pumps, and as the rotating impeller cause drag against the pump casing, drag of the fluid between the impeller and the pump casing, that cause the disc friction losses, waste energy in steering the fluid that does not contribute to output, just like dawamat, like steering. So we can say that the pump total efficiency is often the product of three components: hydraulic efficiency, volumetric efficiency, and mechanical efficiency. Hydraulic efficiency is losses from the fluid motion inside the pump itself. Volumetric efficiency is as a result of the slip losses. Mechanical efficiency is as a result of bearing and friction losses. So if I want to ask a question how we can improve the hydraulic efficiency, how can we improve the hydraulic efficiency? Try always to use smooth impeller designs that will minimize turbulence. How to reduce volumetric efficiency? Always maintain the seal. Should be a rigid seal that will prevent slip. How can we reduce mechanical losses, most important is to use proper alignment, good lubrication to prevent losses of bearing friction. So, in general, the system should match the pump to avoid throttling and oversizing the pump. Now, this is the efficiency and losses curve for centrifugal pumps and for the positive displacement pumps. This is the efficiency. You have a maximum efficiency here for the centrifugal pumps at a specific flow rate and so for centrifugal at this head, for example, we always get this efficiency percentage for the positive displacement pump. You can see that more or less the range of efficiency is constant, and you can see that the head increases, right? Increases. So increasing the head is not affecting the efficiency much in positive displacement pump, but increasing the head is variable with the efficiency, and there is an optimum head which we get the best efficiency, and if we go more than that head, our efficiency will drop. Now let's talk about the best efficiency point, since we are speaking about efficiency. The best efficiency point is where magic happens. Maximum output with minimum waste. Operating far from best efficiency point can lead to vibration, wear, and costly energy bills. So always try to be on the best efficiency point. At the best efficiency point, the hydraulic efficiency is maximum. To ensure proper pump selection, you have to plot first your system curve, and we'll see the system curve, how it looks. After you plot your system curve, the system curve is something like this. The system curve. Okay? After plotting the system curve, which is H against flow, select the pump whose best efficiency is close to your system required flow. For example, this is my required flow, is Q1, okay, and it is corresponds to a head H1, okay. So I will try to select my pump so that the best efficiency will be around this point, around my system flow. The intersection of the system curve and the pump curve should be near the best efficiency point. Like this is the pump curve. This is the pump curve. This is the system curve. And you may have the best efficiency or the efficiency curve of the pump. So this is the best efficiency. You should select your pump such that the best efficiency is around or near your design flow rate. Okay, we will see this better in coming slides. Okay, let's see. This is the efficiency curve for that particular pump. Okay. This is the head capacity curve of the pump, as we explained earlier in many slides. Okay. This curve is a net positive suction head required curve. We will explain it later on. And this is the power requirement curve, which increase by the increase of the flow. Okay, so this is always the best efficiency here, correspond to a best flow rate here, and make sure that your system flow rate is around here. Like you will have your system curve intersect your pump curve. For example, this is my system curve. I don't have it here, but let's see, this is the system curve. So the intersection of the system curve with the pump curve should match or be in the range of a good efficiency, like here. I think this is understandable, right? This is the system curve. This will be like the pump curve. Okay. I hope, like, if the for that pump the efficiency curve is like this, I think this will give you a very low efficiency, is not good selection of this pump. You should select a pump that have an efficiency curve like this, so that the maximum efficiency satisfy your design flow rate. Net positive suction head. Net positive suction head is the bodyguard. I always call it the bodyguard against cavitation. You need to ensure that the suction side of the pump has enough pressure to keep the fluid from flushing into vapor. So net positive suction head is one of the most critical concepts in pump design and operation. It shows whether a pump can safely draw fluid into the impeller without causing cavitation. Okay. Now, net positive suction head is divided into, or we can have, it has a net positive suction head available and required. Like we can have these two key types of net positive suction head. These are types of net positive suction head. Net positive suction head available and net positive suction head required. Net positive suction head available is a system dependent. Your system, your pump system, it is not depending on the pump. It depends on the system. And it is the absolute pressure head at the suction port of the pump minus the vapor pressure head of the liquid. So it is the absolute pressure head at the suction port. We always talk about the suction port, suction line of the pump, minus the vapor pressure of the liquid. Vapor pressure, you know the vapor pressure. The vapor pressure is the pressure at which the fluid vaporizes. Okay, you know the conditions of any liquid to vaporize. Vaporize at certain pressure and at certain temperature. So this is a vapor pressure. So if your pressure at the suction line drops to a point where the pressure reaches the vapor pressure of the fluid, it will turn into bubbles, into vapor, and this will cause us a lot of problem. Anyhow, the net positive suction head available, as we said, depends on the system design. It is the P atmospheric minus the P vapor of the fluid, vapor pressure, over rho g, density and gravity, plus the H static, which is a static suction head. Static suction head and can be positive if the pump is above the tank, and negative if it is below, minus HF. HF is a friction loss in the suction piping. So it is the minimum net positive suction head available to avoid cavitation. Okay. Net positive suction head required is a minimum required by pump to avoid cavitation. Required. Okay. And it is a pump specific. The pump requires this net positive suction head to avoid cavitation. Okay, so it is the manufacturer data that will show you for each pump there is a net positive suction head required. It is the minimum net positive suction head available required to avoid cavitation. Always the net positive suction head available must always be greater than the net positive suction head required to avoid cavitation, to avoid reaching the vapor pressure, to avoid vaporization. Your available in the system suction head should always be more than required by the pump to avoid cavitation. So this diagram will give you clear understanding of the net positive suction head. As you can see here, this is the suction pressure and this is the discharge pressure, and this is the suction and discharge, and this is the I. As you can see here, this curve is representing the flow through this centrifugal pump, where this is the suction, this is the discharge, and this is the eye of the impeller, the center of the impeller. This is the eye. So you can see this is the suction pressure, and here it is positive suction pressure at the inlet of the pump. Then there will be a reduction in pressure due to the suction until it reaches a minimum, which is at the eye. It reaches the minimum at the eye of the pump, then starts increasing at the discharge level. So the red line here is the vapor pressure. So in this case, our minimum pressure is still above the vapor pressure. Okay. So no bubble, because no any vaporization will happen. In this case, we have the suction pressure going, and it reaches the vapor pressure and even goes below. So this means here in this situation where the suction pressure is at and below the bubble formation pressure, what will happen is bubbles will form and collapse at the impeller, and that will cause cavitation and will cause damage to the casing of the discharge of the pump itself. Okay, so cavitation happens. We can say in other words that cavitation happens when the net positive suction head available is less than the required. Okay, so it is required, for example, a net positive suction head is required that will prevent the pressure from reaching the vapor. This is what is required. So if your available is like this, then you are in a risk of vapor bubbles that will form and collapse inside the pump, and noise, vibration, pitting, and pump damage will eventually happen. Net positive suction head available versus net positive suction head required. Net positive suction head available is the actual pressure head available at the pump suction. Calculated as this formula. Net positive suction head available is atmospheric pressure plus static pressure minus loss pressure or friction pressure and the vapor pressure. Okay, so the net positive suction head available, as I always say, should be less than required by the pump to prevent cavitation risk. Understanding the difference between net positive suction head available and net positive suction head required is essential to prevent cavitation and ensure a pump reliability. And again, the net positive suction head available is always calculated by the design engineer who's designing the system, and net positive suction head required is always provided by the manufacturer of the pump. So, like if I want to ask these questions, to have a safe operation and no cavitation, always have the net positive suction head available bigger than the net positive suction head required, okay, to prevent operation, to have a safe operation and to prevent cavitation. If they are equal, then you are at a great risk of cavitation. And if net positive suction head available is less than net positive suction head required, for sure there will be cavitation, damage, and noise. So the question that I want to ask is how to ensure that or how to improve the net positive suction head available, because we always need to improve the available, and we need to lower the net positive suction head required as much as possible. We want to select pumps with less negative suction pressure head. Okay, we need to select the less amount. So to improve the net positive suction head available, what should you do? You can lower the pump elevation so as to use a short suction pipe length. You can also use larger suction pipes, and that's why you can notice in centrifugal pumps that the suction pipe is always one pipe larger than the discharge. This is just to ensure that we are away from the cavitation phenomena. And of course, you can reduce the number of fittings at the suction side to improve this net positive suction head available. And if possible, you can lower the fluid temperature so as the vapor will not occur easily. Like lower temperature means the vapor pressure will be even lower. Okay, and we need to select a low net positive suction head required from the manufacturer, from the pump selection. So this depends on the impeller design, or you can reduce pump speed if it is a variable speed pump. Reducing the pump speed, the RPM, will also ensure a low required net positive suction head, which will prevent cavitation. These are all ways that we can use just to be on the safe side from any danger of cavitation. This is the net positive suction head required. As we said, it is the minimum pressure head required by the pump to avoid cavitation, and it is always determined by the manufacturer, and it depends on the pump design. Okay, and it is always provided in the data sheet. Okay, this is the ways that we just discussed how to improve the net positive suction head available by lowering the pump elevation using large suction pipes, short suction pipe, reduce the number of suction fittings, and how to lower the net positive suction head required. That is, I'm not gonna lower, but from the manufacturer point of view, they should use low impeller design. From my view, I can use, if it is a variable speed pump, I can reduce the pump speed. And this curve is very, very, very important. It shows you the net positive suction head in general compared to the flow rate. The yellow one is the required pressure, and the green one is the available, required by the manufacturer, by the pump to work. Available is as per your system design. And you can see as your flow increases, you should always go for higher required pressure, higher pump, higher net positive suction head required pumps. Okay, and as you can see, also as the flow increases, then the available head will decrease, which is not good. Okay, now at this point we are in a great risk, as we stated in the last slide. When the net positive suction head required is equal to the negative positive suction head available, we are in a big risk of cavitation, because if we increase the flow rate a little bit more, we are in a cavitation zone. Okay, so always make sure that you are on the safe zone always. Okay, so this is the safe zone, and you can see that always the net positive suction head required is always below the net positive suction head available. Okay, so this graph is very important for you to understand. Now let's talk about the cavitation phenomenon. Cavitation is a silent killer. It sounds like gravel in your pump and leaves pits on your impeller. We will explore why it happens, how to hear and see it, and what system tweaks help eliminate it. So it is a destructive phenomenon. It occurs when the suction side drops below the fluid vapor pressure, and it causes the liquid to vaporize into bubbles. The symptoms: when you hear noise or the pump is vibrating, that you feel there is a damage to the impeller and the blades, and you can prevent it simply by this very simple equation. Always ensure that your net positive suction head available is greater, not equal, greater, because equal is a risk, greater than the net positive suction head required. the process of cavitation, how it happens. First, there will be a low pressure at the suction eye. We describe what is the eye, the center of the impeller. So there will be low pressure. Low pressure will reach the vaporization pressure of the fluid, then bubble will form. Bubble will form and will collapse. The collapsing of the bubbles, because they will be compressed by the impeller. Impeller is designed to rotate and to give energy to fluids, liquids, not to fluids of gases. So what will happen is that the bubbles will collapse. Collapsing will cause pitting, damage on the skin of the pump from inside. It will cause shock and erosion. On a pump curve, cavitation tends to occur at high flow rates, as we just discussed, where the net positive suction head required rises quickly. If your system's net positive suction head available curve crosses below the required, cavitation is likely to happen. This is a picture of cavitation. As you can see, this is the impeller, and this is the damage that happens on the impeller and on the surface of the pump, the inner surface. So when these pittings, we call these pittings, when these pittings happen, usually a noise will happen, drop in pressure, because this is very rough area. High drop of pressure will happen, excessive vibration, because now the wheel will not be balanced, so it will be in a vibrating mode. So we always try to avoid cavitation as much as possible, so we will not lose our pump. Let's see the reciprocating pumps and how is the net positive suction head related to reciprocating pump. In the last few slides, we described the relationship between the net positive suction head and centrifugal pumps, but now let's see how this is related to reciprocating pumps. Reciprocating pumps create pulsation because it's like a piston in a cylinder, so it's like pulses, like a heart pulses, okay, like pushing and pulling, pushing and pulling. This is a punchet. Those affect the net positive suction head. When suction pressure dips between pulses, of course, you will risk flashing and vapor flux. All happens when the suction pressure goes very low. This will cause flashing. Flashing is a process of turning from liquid to vapor. Reciprocating pumps are type of positive displacement pump. One of them is the reciprocating pumps, and they are typically used in high pressure, low flow application. These pumps handle fluid by what? By trapping a fixed volume and pushing it through the discharge. That's why we say that the positive displacement pump are working on constant flow rate but varying head. When dealing with net positive suction head for reciprocating pumps, considerations are different from centrifugal. Why? Because of the pulse weighting phenomena. Non-uniform suction flow. In centrifugal pump, your suction flow or suction pressures are uniform, but here they are changing. Why? Why? Because the piston itself is in acceleration. How? Because it starts from zero velocity, reaches to the maximum velocity at the center of the stroke, and eventually reach a zero or deaccelerate from the maximum velocity to a zero when it compress all the fluid to the suction valves, and the suction valves will open. So
This means that there is an acceleration here. That's why the flow is not uniform. Net positive suction head must be carefully ensured in the positive displacement pump to avoid hammering at the suction valve. In the centrifugal hammering, as we saw in the photo, it happens on the impeller or in the casing. Here it happens on the suction valve. Okay. Also, we will have vapor lock. What do we mean by vapor lock? Is like we are compressing vapor in the case of a positive displacement pump, because if flashing happens, then you will have vapor, and then when you are compressing, you will compress the liquid with the vapor, and this will make this vapor lock, and this vapor lock will cause a lot of damage. It might break your pump. And of course, we need to avoid this vapor so that there will be no flow interruptions and no mechanical wear. So for the net positive suction head required, which is provided by the manufacturer, the curve should be based on the pump speed, plunger size and stroke, and suction valve type. These three variables are controlled by the manufacturer. They use these factors, combination of these variables, to provide a net positive suction head required for that pump. Because of the suction acceleration head, as I just mentioned, the available net positive suction head must account also for suction line friction, static suction lift, plus what acceleration head, okay, which is due to reciprocating pumps because there is acceleration. Okay, so the suction acceleration head, because of the suction acceleration head, the actual available net positive suction head must account for the friction, static suction head, lift, plus the acceleration head. So the net positive suction head available is given by this equation: pressure, atmospheric pressure, plus static head, plus friction head, minus friction head, always minus acceleration head. This is a new term and it is in a minus the vapor pressure. Here the acceleration head, it depends on the fluid mass, pipe length, and speed. Acceleration head can significantly reduce the net positive suction head available. Okay, can reduce it because it is a minus sign, so it will get in a reduction of this net positive suction head, especially at high speeds. Okay, because at high speeds, high acceleration, also at long suction lines, also will have high acceleration. So this acceleration head, you can find it only in the positive displacement pump. Net positive suction head available in reciprocating pump. You can see this is the reciprocating pump and this is the stroke. So we have the acceleration head due to the acceleration of the fluid. We have the friction head. We have the hydraulic head, and this is the atmospheric pressure head. Okay. So now let's go through quick quizzes. If net positive suction head available is less than net positive suction head required, what will happen? Sure, pump will suffer damage, right? Cavitation. Here in this example, it's giving that at 25 degrees centigrade, the P vapor is 3 kilonewton per meter square, P atmosphere is 105, lift is 7.5, friction loss is 3.2. So if you want to calculate the net positive suction head available, we will use this formula and you will get this value. A quick summary: pump performance curve. We have, these are the essential or the basic of the pumps. If you understand the head Q curve, you are halfway in selecting the pump, as I said in the first slide. And we see how it varies, the head and Q in centrifugal compared with positive displacement pump. We also show how the power is calculated and the efficiency, and you have to select your pump so that the maximum efficiency of the pump matches your design flow rate. We talk about the net positive suction head. Why we need to consider net positive suction head? Because of cavitation prevention, and we say that there are two types of net positive suction head, available and required. The available is by the system design or the existing system, and required is stated by the manufacturer, and you should always have your available more than the required to prevent the cavitation. And we should always design near the best efficiency point for efficiency of the pump and reliability and long lifespan for the pump. Here are some diagrams for the centrifugal pump. In this diagram, this is the pump curve, relationship between head and Q. This is the efficiency curve. So if your flow rate is in this range, maybe it is 9, 10, 10.5, your flow should be 10.5 to work on a best efficiency, on a peak efficiency. And of course the horsepower will increase by increasing the flow rate. Okay, and this is where we have your system curve, existing system, the design system. It cut with the pump curve where they intersect. You should make sure that at your operating flow rates, your pump efficiency curve should be at the maximum, okay, to have efficient pump running with long pump lifespan. Thank you.